All right, so we will continue from where we left off a couple weeks ago. So we are now into part two of single phase transformers. So you would recall that in part one, we had looked at the ideal transformer, um, turns ratio, which was equal to voltage ratio. Um, and this turns ratio was the primary turns divided by the secondary turns, and that was equivalent to the primary voltage divided by the secondary voltage, uh, and also the secondary current divided by the primary current. So those relationships gave you were equal to the turns ratio. We also looked at maybe in some detail at the ideal transformer. So those ratios came primarily from the ideal transformer. And then we started to explore the fact that the transformer wasn't really ideal. So it didn't only have just primary winding with no impedances or secondary winding with no impedances, but we now have to model using schematic diagrams the fact that the transformer has core parameters, so parameters that are representing the magnetic core made up of some kind of ferromagnetic material. And we said that those core parameters included the core loss resistance, which was basically representing the losses that took place due to eddy currents and hysteresis in the core. And then we calculated the core loss current, that current now that would supply the losses, and the magnetizing current, that current that would provide the magnetizing flux that would induce an EMF in both windings. And significant to us is the fact that we could energize the primary winding and get a voltage in the secondary winding, which was available for use. All right. So we will continue from there. And today now we will look at these topics. So we're going to be looking at the equivalent circuit of the transformer, and then you will realize now that there are actually three different types of equivalent circuit. One is the exact, which I introduced to you a couple weeks ago, and then we can approximate it, and then we can even further simplify it. So we'll be looking at those, and then we'll be doing some calculations, not very difficult. Later on, we'll get into voltage regulation, and then there are a couple exercises for you to do in class and some for homework. All right, so we start out with all the words. All right, and as I said just a while ago, we can model the transformer by using some equivalent circuit or schematic circuit diagrams. So the three types, as I mentioned before, the exact equivalent, the approximate equivalent, and then the simplified equivalent. So in a little while, I will show you two other circuits, the exact and the approximate. And while I will show you them, I'll just point out maybe some of the differences, the obvious differences that you will see as you look at the diagram. So on the left here is the exact equivalent. So the supply voltage is represented by V1, and then you have the winding, the primary winding represented by a winding resistance R1 and a winding reactance X1. And then this is the core parameters that we looked at the last time. So the core loss resistance and the magnetizing reactance. And then you have the no load current, which once the transformer becomes energized, whether load is on it or not, the core will be drawing this no load current to supply the core losses and the magnetizing current. All right. And so in dotted line here, you have the ideal transformer, which was what you would have been used to from high school days. And on the secondary, we have the secondary winding with resistance and reactance also. Now, so that's the exact equivalent. Now, on your right, you will notice that the circuit appears to be simpler. And basically what has happened is that we have taken out the core parameters. So the core parameters have been removed to give us an approximate equivalent circuit. And we can do that because, as you saw a couple weeks ago, the no load current is very small. So that current, can a person mute their mic? So that current is approximately 5% of full load current. All right, it won't be more than 5% of the full load current. So, you know, if we want to make some quick approximation, we can remove that without too much loss of accuracy. All right, and it will, as you can see, simplify our analysis of the circuit. All right, so the difference between the exact and the approximate is that the core parameters have been taken out. And we said there will be some loss of accuracy, but it won't be very significant. All right, more words. So in the next slide or so, I will show you now the difference between the approximate equivalent circuit and the simplified equivalent circuit. And let us just look at it. So the approximate, notice no core parameters here. And then the simplified equivalent. Notice now that there is nothing on the secondary. No winding with impedances, resistance or reactance on the secondary. So we have shifted over everything on the secondary over to the primary. This is actually called referring to the primary. So we have referred the secondary impedances to the primary. All right. So notice now that the resistance is now RE instead of a R1 and a R2. It's an equivalent resistance. And the reactance on the primary side now is an equivalent reactance, XE. All right. So no winding parameters on the secondary. Everything has been referred to the primary. And we will show you in a little while that these two circuits, although they look different, can be made equivalent. Right. But as you will see now, we have basically reduced our transformer to an impedance, ZE. Right. So instead of two sets of impedances, we have now reduced it to one, and that will simplify our calculations even further. And especially for those who are doing power system, this is what you'll be talking about when you're talking about the impedance of the transformer. When you're thinking about per unit, you would change this value into a per unit or a percentage value. All right, so what we want to do now is to look at the approximate equivalent circuit first. Then we're gonna be looking at the simplified one afterwards. And we're gonna be comparing them because we must make sure that both of them are actually equivalent. All right, so how we're gonna analyze it is by looking at the real power losses in the windings for this approximate equivalent circuit. So real power through a resistor, remember now, would be I square R, right? I square R. So on the primary side, so the transformer is loaded, right? So that's why you have a secondary current too. So on the primary side, the power drawn by the primary winding, the real power drawn by the primary winding would be I1 square R1. While on the secondary side, the real power drawn by the secondary winding would be I2 square R2. So therefore, the total power drawn by both windings would be I1 square R1 plus I2 square R2. All right. Clear so far?
Yes, sir.
Okay, yes, sir. Good. All right, so now let us look at the simplified equivalent one now. So the circuit now where the winding parameters have been referred to the primary, referred from the secondary to the primary. All right. So we now have one equivalent resistance on this circuit here. So the power drawn by that equivalent resistance would be I1, so I1 is going through it, I1 square RE. All right. But we know that this equivalent resistance has both the primary winding resistance and some component of the secondary winding resistance included in it, right? So that component of the secondary winding resistance is called R2 prime, and R2 prime is the referred secondary winding resistance. All right, so the total power drawn by this simplified equivalent circuit then would be I1 square RE. All right. Now, if the two circuits are equivalent, then the total power drawn by the simplified would be also equal to the approximate. All right. So equation 1 would be equal to equation 2. And just a reminder, this was equation 2. And before that, this was equation 1. So these two equations are equal. right, so therefore, I1 square R1 plus I2 square R2 is equal to I1 square RE. And then if we expand out for RE, it will be equal to R1 plus R2 prime. And then you multiply all of that by I1 square. So equating, we see that I1 square R1 is on both sides of the equation, so that can be cancelled. So therefore, we are left with I2 square R2 equal to I1 square R2 prime. Right. And from this, we can make R2 prime the subject of the formula, so we can calculate what R2 prime is, that referred secondary impedance, resistance. We can just manipulate this equation. So it's I2 square R2 divided by I1 square. Now, since I2 and I1 are both square, then we could just put them in a bracket and square and put the square outside. And if you will recall, I2 over I1 is equal to A, the turns ratio. So R2 prime now becomes A square times R2, right? All right, so the referred impedance, resistance referred from the secondary winding is now equal to the turns ratio square times that value that it had when it was over on the secondary. All right. So referring from the secondary to the primary means that we multiply that secondary value by the turns ratio square. So similarly for the reactance, if we consider the reactive power drawn by both circuits, then X2 prime would be equal to A square times X2. All right, so it's a similar kind of thing. Yeah, all right, let's just say it like that. All right. So now we have the equivalent resistance is being R1 plus R2 prime would be equal to R1 plus A squared times R2, and XE would be equal to X1 plus A square X2. And then equivalent impedance would be RE plus JXE. All right.
Sorry, quick question. Can you just re-explain what R2 prime what it represents?
Yeah, man. All right. So right here on the previous slide, R2 prime is the referred secondary winding resistance. All right, so let's go back over here. So here, so we're going back a little. So here we have a secondary winding that has a resistance R2 and a reactance X2. Now, when I move this secondary winding resistance over to the primary, when I refer it to the primary, it becomes R2 prime. All right. So
Okay,
just to
sir.
keep track of the name, I put a prime on it. And I do the same thing with the X2. I put a prime on it when I bring it over. All right. So R1,
Yes, sir.
good. So R1 plus R2 prime would be the equivalent resistance on the primary. And similarly, XE would be X1 plus X2 prime. All right. For XE, this when I referred the turns ratio it can also be written in terms of N1 over N2 for the reactance. All right, but we won't bother get into that. So it's not only just I2 over I1, but it could also have been written in terms of N1 over N2. Right. And that comes from our relationship for inductance. L, you might remember it. L is equal to N phi over I, something like that.
Yes, sir.
Right. So I could have written X2 in terms of that kind of relationship and get the same thing though. So, but instead of I2 over I1 as I have here, it would be N1 over N2. All right, but you don't have to worry too much about that. What's important is that when we're moving from the secondary to the primary, we multiply by the turns ratio square, and when we move from the primary to the secondary, we actually divide by the turns ratio square. So if I had put all the primary winding impedances, if I had put these over onto the secondary, what I would have been doing what I would have to do is to divide by the turns ratio square. So referring from the primary to the secondary means I divide by the turns ratio square. All right, so here is something for you to do. Simple one. And I've written down the answers already too. So this shouldn't detain you more than 5 minutes. So I want you to work this out, see if you get these answers. So a transformer has 600 primary turns and 150 secondary turns. The primary and secondary resistances are 0.25 ohm and 0.01 ohm respectively. And the corresponding leakage reactances, which are the X1 and the X2, are 1 ohm and 0.04 ohm respectively. So X1 would be 1 and X2 would be 0.04. So we should find the equivalent resistance referred to the primary, the equivalent reactance referred to the primary, and the equivalent impedance referred to the primary, and the phase angle of the primary impedance, of that impedance. All right, so 5 minutes. Everybody clear what they need to do?
Clear enough, sir, I think.
All right, good. All right, so 5 minutes.
Sir.
Okay, so I'm sure everybody got this. Yes? No?
Yes, sir.
Okay.
Yes, sir.
All right, good. Anybody had any challenge with it?
No, sir.
All right, good. All right, so we can move on then. All right. All right. So we're coming to the voltage regulation of the transformer. All right. And the voltage regulation basically means that when I put a load on the transformer, the voltage will change, right? I put a load on the transformer, the voltage will change. So if it is like a lagging power factor load, the voltage will actually decrease, right? At the terminals here, right? So just loading going to bring down the voltage, especially for a lagging power factor load, right? Now, what we want to do is to see, when we're thinking about voltage regulation, is how much that voltage will change. When we compare it to from no load to full load. So at no load, we expect a certain value. Let's say 400 volts. At full load, the voltage may drop, may fall down to 380. Right? What we want to do is to see how the transformer will actually behave under load situation, how much the voltage will actually change from no load to full load. And that is the definition for voltage regulation. So it's a change in the transformer secondary voltage from no load to full load as a fraction or percentage of the no load voltage. All right. So suppose that the secondary voltage, the transformer is rated, Mr. Brown. All right, so the transformer is rated, say, as we say, at 400 volts. And so it should be delivering 400 volts at full load, right? So imagine now that it is carrying full load. When you, if there's a switch here now and you open that switch and remove the load, you will find that the voltage at the secondary end, at the terminals here now, will actually increase. All right, so we want to see that change. Okay, Mr. Brown. All right, so we want to see that kind of change mathematically, because by law, they call it statutory obligations, you cannot have your voltage change beyond a certain percentage of rated or nominal. In Jamaica, it is by law 6%. You can't go more than 6%. At least when I was at JPS, that it was. And then JPS used to try to maintain it within 5%. So there's a legal requirement to make sure that your voltages are within a certain level, value or percentage value of your rated or nominal voltage. So calculation for voltage regulation will help us to determine whether or not our transformer would be meeting the statutory requirements. All right, so let's get into the calculation or the derivation for this voltage regulation. All right, and we can use our simplified referred circuit to do this. It helps significantly in simplifying the calculation. All right, so I could write, so previously I wrote it as V2, but if you see on, for this circuit, E2 and V2 are the same values, right? By the way, E2 is the voltage across the secondary winding, and E1 is the voltage across the primary winding. And there's actually a difference between E1 for unload. There's actually a difference between E1 and V1 on load. When there's no load, E1 and V1 are the same. All right, so bear that in mind. When there's no load, E1 and V1 are the same. But right now, the difference is due to the voltage drop across the impedance here. All right, so E1 plus I1 ZE would be equal to V1. All right, everybody can see that? V1 would be equal to I1 ZE plus E1. All right, so yeah, let me is that clear to everybody?
Sir, one more time, sir.
This voltage here, the supply voltage, would be the sum of this voltage drop across the winding plus the voltage, that induced voltage across the primary winding. So V1 would be equal to I1 ZE plus E1.
That is at full load.
Right, at any load, right? Because at no load, then I1 theoretically is 0. So then V1 would be equal to E1.
Okay.
All right. All right. Yeah, but when we're comparing voltage regulation, technically we should be looking at the secondary voltage. All right. I said technically because I will explain in a little while that we can actually use the primary voltages also. All right, so E2, as you can see from this circuit now, E2 would be equal to V2, since there are no voltage drops across any winding here. Right. So I could write it as the voltage regulation as E2 no load minus E2 at full load, and then we divide it by E2 at no load. So that's in per unit, or if we want to find the percentage voltage regulation, then we multiply that by 100%. All right.
So this formula is similar to percentage error formula.
Yeah, similar. All right. But the voltage regulation can also be written in terms of the primary voltages. So when turns ratio is taken into consideration. All right, but I won't bother do the derivation right here. But you can, from what we spoke about a while ago, V1 would be the no load voltage. All right. And so E1 would be equal to V1 at no load. At full load now, the voltage here across here now would be E1. And that V1, E1 then would be equal to, as I said before, was V1 minus I1 ZE. All right, but you can read through this, but we will do some calculations shortly to show it more clearly. All right. All right, so I'm making the point here that E1 is the primary voltage at the input terminals of the ideal transformer. So remember here, this here enclosed by the bracket here is representing the ideal transformer. All right. All right, so if I do some more derivation, I can come up with a formula for voltage regulation being distilled down to I1 ZE over V1 rated. All right, but I prefer to use this one because you'll get more accuracy here. All right. But the mathematics will lead you to this also. All right. And since we need to compare to secondary voltage, we can write that secondary induced EMF as the E1 divided by the turns ratio. All right, so don't get too bogged down with this yet. We're gonna give an example right now, and that will show you how we apply it. All right, so let us look at the example, and then if there are any questions afterwards, we can try to clarify it. So we have a 100 kVA transformer, which has 400 turns on the primary and 80 turns on the secondary. The primary and secondary resistances are 0.3 ohm and 0.01 ohm respectively. And the corresponding leakage reactances are 1.1 ohm and 0.035 ohm respectively. The supply voltage is 2,200 volts, and we should calculate the equivalent impedance referred to the primary circuit, the voltage regulation, and the secondary terminal voltage for full load having a power factor of 0.8 lagging and 2.8 leading. All right, so we're gonna be looking at the 0.8 lagging power factor load. All right, so our turns ratio, since we're gonna be using it, we need to calculate it 400 N1 over N2, 400 over 80, and that's equal to 5. Now, since the transformer is delivering full load, and when you do your voltage regulation calculation, you want to assess what the transformer is doing at full load. Right. So at S is equal to V1 I1. Remember that from a couple weeks ago. So I1 then would be equal to S divided by V1. And that works out to be 45.45 amps. So that's the primary full load current. All right, now, so we are solving for 0.8 power factor lagging. So the full load is the power factor at that full load is 0.8 lagging. All right, now technically and theoretically, that lagging power factor is on the secondary side of the transformer because the load is on the secondary. So we're gonna make an assumption that the power factor is also 0.8 lagging on the primary side, right? And it can work if we don't include the core parameters. The assumption is we can make that assumption safely if since we're not including the primary core parameters, then the power factor on the secondary side can be assumed to be the power factor on the primary side. So therefore, that power factor angle is minus 36.87 for 0.8 power factor lagging. So therefore, I1 would be at 45.45 at angle minus 36.87 degrees. All right, so we know what I1 is. What we need to do now is to work out what ZE is, the equivalent impedance. So we're gonna start by working out what the equivalent resistance is. So, and that is R1 plus A square R2, and R1 was 0.3, R2 was 0.05, A was 5, so A square. So RE is 0.55 ohm. All right, so this is just basically more practice for what you did just a while ago. All right, similarly, ZE, X1 plus A square X2, and X1 is 1.1, X2 is 0.035. So XE is equal to 1.975. So answering question A now, the equivalent impedance referred to the primary would be RE plus JXE, and that would be 0.55 plus J 1.975, and that is 2.05 at angle 74.44 degrees. All right. So now we want to find what the voltage is.
Sir.
Yes. Sorry.
When do you divide by A again? By A squared?
If you're referring from the primary to the secondary.
From primary.
So you're moving left to right instead of from right to left. It's something that you can derive to, you know. So if you have an issue memorizing it or remembering it, you can also derive it for yourself. Just as we did moving the secondary parameters over to the primary, you can do it also, but this time move the primary to the secondary, and you will find that you're actually dividing the primary winding impedances, the resistance and the reactance by the turns ratio square when you move it over to the secondary. All right. All right. So we're going now. We want to find E1 here, because when we find E1, then we can find what E2 is. And remember, when you're doing your voltage regulation, you actually want to see what the secondary voltage is actually doing, right? So we're going to find E1 and divide it by the turns ratio to give me E2. All right, so how we find E1 now? Remember, V1 is equal to I1 Z1 ZE plus E1. So V1 is equal to I1 ZE plus E1. All right, so if we manipulate that equation, we E1 then becomes V1 minus I1 ZE. All right. Now V1, the rated value is 2000, right? And it is now our reference phasor. The supply voltage is our reference phasor here, right? So E1, substituting the values, will be the 2200 at angle 0. And then I1 will be the 45.45 at angle minus 36.87. And ZE will be the 2.05 at angle 74.44. All right, so E1 works out to be, so E1 loaded would be 2126.91. All right, so at no load, it would have been 2200. Once the load is on the system, it falls to 2126.91. All right, so we want to find what E2 is now, since we want to find the voltage regulation. So E2 at full load would be E1 at full load divided by A. All right, and that works out to be the 221.26.9 divided by 5. So that works out to be 425.38 at angle minus 1.53 degrees. All right, so E2 at full load is 425.38. All right, now at no load, based on the turns ratio, V2 should be equal to V1 divided by the turns ratio. So that should be 2200 divided by 5, and that'll be 440. So therefore, the voltage regulation now will be the no load voltage on the secondary minus the full load voltage on the secondary divided by the no load voltage on the secondary. All right, so notice here now that we don't use the angles. We just use the magnitudes when you're working out the voltage regulation. So you reach up to this point here where you have the angle, but then when you're working out the voltage regulation now, come back, we don't use the angles in the voltage regulation formula. All right, so it's just the magnitudes. So at no load, it was 440. At full load, it's 425. And then that works out to be this value, 0.0332 per unit. Or if we were to write it in percentage, it would be 3.32%. Let's multiply this per unit value by 100% to give you 3.32. All right. Any questions on that? Or is it clear? Straightforward?
Oh, sorry, it's not straightforward, but you get in there.
You get in there? All right. I'm going to give you a chance to get there very shortly. All right. Yeah. Yeah. Here is one for you to practice right now. So I'm going to give you maybe about 20 minutes to go and practice. So you can write down the data here. And if you want me to go back to anything, you can let me know.
All right, sir.
All right, so this one just wants you to determine the secondary voltage at full load. So it's not asking you to calculate the voltage regulation right now. But once you have the secondary voltage at full load, you can work out what the voltage regulation would be. All right, so the question says that we have a 10 kVA single phase transformer, which have a voltage V1 2000 volts and V2 400 volts at no load. And it has resistance and leakage reactances as follows. Primary winding resistance is equal to 5.5 ohm and the reactance is equal to 12 ohm. The secondary winding resistance is equal to 0.2 ohm and the reactance is 0.45 ohm. So you're asked now to determine this approximate value of the secondary voltage at full load, 0.8 power factor lagging, when this primary supply voltage is 2000 volts. All right, so about 15 minutes.
Sir, one question.
Yeah,
E1 was V rated minus I1 ZE.
right.
Yeah. Okay, all right.
Let me go back here.
All
This is
right.
what you're asking about, right?
Yes, sir. Yeah.
Sir, you can go back to the circuit for a second.
No problem. This one?
Yes, sir.
Yeah.
Sir? Mr. Daly?
Yes, I'm here.
Sir, could you show back the question, please?
No problem.
Not this one, sir. The one we're working on now.
Isn't this one? Isn't this the one we're working on now?
Oh,
Yes, sir. That's what we're working on now.
this one. This one. Yes, sir.
This one, right?
Yes, sir. This one.
Okay.
So I got the answer, sir.
Oh, good, good. Oh, let me see, who was that?
So
Who?
Adams, sir.
Adams.
Yes, sir.
Okay. All right. Very good.
Sir, I got it as well, but there is still something unclear.
There's still something that.
Sir, I have a question because there is still something unclear to me.
Okay. Yeah, man. Go ahead.
Sir, the question is in regards to the simplified circuit.
Mhm.
Sir, when you say a referee to the secondary, right, is because of how the circuit is, because at no load there is no windings on the secondary. Why you would refer it?
No, man. All right. Basically, let's go back to that circuit. Let's go back to those circuits. All right. So, yeah, let's go way back. All right. So we could use this one. You will notice that we have so the transformer, as you know, has two windings. The two winding transformer that we are used to has
Yes, sir.
two windings, a primary winding and a secondary winding, right? So
All right.
it will always have it. Now, what we're doing is to use mathematics to model the transformer, right? Using our electrical circuit diagrams. So we're modeling the transformer now to see if we can work out what the transformer is doing. So we know that if we put certain load on it, we're going to get the voltage. For example, if you had a transformer like the one we had in the problem, and you put the same amount of load on it, the same type of load, you would have gotten the voltage that you got, right, at the terminal once you load it.
Oh, okay, sir. Because I realized that at full load, the voltage would really be less than before.
Right, than the rated. Right.
Right.
So and yeah, that is that is what we're trying to show, that once you load the transformer, so in reality, that is what will take place, right? So those transformers are on the poles outside of your house, outside of your gate, on the line. Load take them, the voltage will fall. So at your home, you might see low voltage sometimes, right? If too much load is on the transformer. Say the transformer is not properly sized, or load increase over time and they did not change the transformer, then you will start to see low voltages on the at your house. All right. Now, the transformer can be regulated to correct that, right? So that is why we're actually doing the voltage regulation calculation to show you that, yes, in reality, once you load the transformer, the voltage will fall, right? But we can actually make some adjustments to minimize that drop in voltage. All right. So when we back to the question that you were asking now about why we refer, basically what you have here is you have two windings, right, across the core, and this what we want to do now is to see if we can simplify. So we have two sets of impedance. We have a primary set of impedance and a secondary set of impedance. Now, if we can simplify this and get one set of impedance, our calculations, as you saw a while ago, have significantly simplified, right?
Yes, sir.
So basically, that's what we're trying to do. So what we're doing is to electrically and mathematically simulate what the physical transformer would be doing by drawing these diagrams and basically modeling what a real transformer would be doing. So we move the winding, the secondary windings, and put them over onto the primary. But we could just have moved the primary windings and put them over on the secondary. It really doesn't matter. It really doesn't matter which side you put it on. So we have chosen to move the secondary and put them over onto the primary. And you will find most problems in textbooks asking you to do something like that. All right. If we were in the lab still, you would find so that is what we eventually would be doing also. So it is just a convenient way. Basically what we want to do is to reduce those three sets of impedances on the transformer down to one impedance. Basically that's what we're trying to do, so we can simplify our calculation. If you remember when we did power systems 2, Mr. Bruce, if you remember when we did power system 2, we eventually had, in the power system, we had transformers being represented as just one single impedance. And in fact, just a reactance, right? Because the resistance would be relatively low compared to the reactance for power system level transformers. Right? So we can actually get this down to one equivalent impedance, which is what we're trying to do here. Right?
Yes, sir. I get it.
Okay, good. All right.
Sir, before you move, sir, go back to the diagram. We just try to see if we get it, the fullest of what we're doing. So at no load, all our voltage drop across the primary coil. So and then all of the voltage is transformed based on the turns ratio, right? No,
right. So hold on, let me stop you 1 second here. So at no load, I2 would be equal to 0, right?
Yes.
I2 would be equal to 0. Now, based on that turns ratio thing, I1 would also be equal to 0, right?
Yeah.
Right. So if I1 is equal to 0, then V1, which is equal to I1 ZE plus E1, you would have no voltage drop across the winding here.
Right.
Right? So V1 and E1 would be the same. Right?
So,
and then E1 and E2 would be related by the turns ratio.
turns ratio.
Right. So E1 and E2 are always related by the turns ratio. All right. So E1 divided by E2 would be equal to A.
Yes.
Right. So whenever whether it's loaded or not, E1 divided by E2 would be equal to A. All right. So on no load, E2 would be the rated value because no load is there. So you expect the transformer to be delivering or to be capable of delivering its rated voltage on no load. All right. Now so if this is rated value by the turns ratio, this would also be equal to the primary voltage. E1 and V1 would be the same, right? Because remember, the turns ratio is actually V1 divided by V2.
Yes.
With me? The turns ratio is V1 divided by V2. But on no load, V1 is equal to E1 and V2 is equal to E2 on no load. Now, when a load comes on, all right, so that clear?
Yes, sir.
All right, so when a load comes on now, then you're going to have current flowing and you're going to have a voltage drop. All right. What we have done is move the impedances from here and put them over here. Right. So the voltage drop that we will actually be calculating now would be as if everything is, all the winding impedances are on the primary. So we see 1 voltage drop across the primary winding here. Since we have referred the secondary parameters to the primary, then the voltage drop now due to the load current would be across the winding here. So Mr. Wilson, you sound very excited, man. You can turn off your mute your mic for me, please.
So sir, basically it's the current that is produced by loading is cause the voltage drop,
Right,
which in turn reduces the output voltage.
right. So the voltage drop is actually taking place in the windings.
Yes. All right, sir.
All right, good. All right, so everybody, I want to say something more about this, but I just want to make sure everybody is has solved the problem by now. How are we, others?
So
Yeah.
it's still not getting the solution.
I get something right, yeah.
So Mr. Duncan says still not getting it.
No, sir.
All right. So let's look at the approach then. So you had worked out what your full load current would be?
The full load current. So that would
On the
be
primary side, right?
So that would be the apparent power divided by the V1, right? So that
Right.
would
The primary voltage, good. Right.
so 10,000 divided by 2,000,
Mm-hmm.
and I get 5.
Right. So that's the magnitude of the primary current, right? Or the full load primary current. All right. So, but we have to take into consideration the power factor. All right. So that's why this is not the same problem. This is the example we looked at before, but it's basically the same approach. All right. So our primary current then would be 5 amps at angle minus 36.87. All right. When you take into consideration the power factor. Everybody have that?
Yes, sir.
So Mr. Gray has it.
Yes, sir.
Yes, sir. Yes, sir.
All right, good. All right, so what is your equivalent impedance?
Sir, I got 25.51 at an angle of 65.695.
All right, okay, yeah, good. All right, so after that now, what do you do?
So V1 or the load, this is the primary voltage at full load. So this will be equal to it's I1ZE. Oh, it's V1 minus I1ZE. So
Right.
yeah, so okay, I see where I went from now, sir.
Right. So remember, you want to find the voltage across the here, right? Across the winding. So that is E1. So we want to find this voltage, and basically that is given by this formula. All right, so if you substitute the values now, V1 would be 2000 at angle 0. That's V1 rated. And then I1 would be 5 at angle minus 36.87. And ZE, as you said before, is 25.511 at angle 65.7 approximately. So E1 works out to be 1889.256 at an angle of minus 1.87.
Yes, sir, getting the solution now.
Okay. Okay. All right. So if you divide that 1889 by the turns ratio, you will get what E2 is equal to. All right. So I imagine everybody's okay there now. If anybody's still having any problems, you can let me know now. All right. So can we go on? We'll be just here for another couple minutes. All right. Now we saw where this transformer, which is rated to give us 400 volts on the secondary, was actually giving us 377 when it was loaded. All right. Now, how power transformers work is that they actually have a voltage regulator installed on the primary side of the transformer. All right, so a voltage regulator is connected to the primary winding turns, right? Now, to make sure that we have 400 volts out here, when it's fully loaded, we would actually have to raise the value of E1, right? By a few percentage. So let us see what it 400 minus 377. So about 5%, right? The voltage regulation will be about 5%.
Yes, sir, thereabouts.
Right. So what will be done now is that we would have to raise the primary voltage by about 5% of its rated value to increase the secondary voltage to give you the 400 volts, right?
Sir,
Yes.
could we have added a capacitor?
Where?
Beside the inductor on the left. To
Beside
reduce. Yeah.
Yes, sir.
beside the inductor? You mean here?
Yeah.
And no, it's actually it wouldn't be done here. Remember now that the transformer is an enclosed device still, right? What would actually be done though, what could be done, what could be done is that you could connect a capacitor in parallel with the load here, right? So it is all, so the capacitor could supply the load, right? And reduce the demand coming from this side of the supply. But the transformer now is an enclosed device, so it would be inside a container, so you wouldn't be able to go on and now connect a capacitor across it like that. So how the regulation is actually done is that you have a device now that can actually adjust the amount of windings that are connected to the supply, right? And that is called an automatic voltage regulator. So when the voltage is starting to get low, then it allows more of the primary turns to be connected to the supply voltage, right? So that is basic. And so as we see now, the voltage regulation will be about 5.5%. Would actually now have to raise the primary voltage by admitting more turns into the to be connected to the supply voltage. So increase the voltage on the primary windings by about 5%. So that would be, it was what before, 2000. Right, 2000. So right. So the voltage regulator would actually raise the primary voltage up to about 2100 to allow you to get 400 volts at the secondary. So this is something that is actually going on, and it is going on continuously. So as adjustments on the load need to take place within a certain band, the transformer regulator, voltage regulator, would adjust to meet the change in load to give you your rated voltage, right? So in reality, bear this in mind, that in reality now, the adjustment to make sure that you get your 400 volts at full load would be done on the primary side of the transformer by raising the amount of turns, winding turns that are connected to the supply. So we'll have to actually raise the voltage of the supply now to 2,100 to give you 400 volts on the secondary. All right.
Sure, that means you have to do maintenance on that on the transformer because of those movements, continuous movements.
Yeah, usually on those big power transformers, they are maintained usually once a year. So it wouldn't be only the voltage regulator that they will be looking at. But they will be looking at the oil inside of the transformer. To change it just to make sure so there are no deposits of say carbon in the oil. So yeah, general maintenance would be done on the transformers. It's a once a year, especially for those that are usually highly loaded. Okay. All right, so I have put two questions here. The first one is a very simple one. The second one may be a little bit more challenging. I have put the answers here. Answer here for this question. I didn't put it in the slides that I sent to you earlier. And I put it here because the answer in the book is gonna be different from this. So you want to know that you're actually on the right track. So write down this answer for question 24. All right. And yeah, try to practice the questions in the textbook, both textbooks. You have the Wiley too. There are questions in there also. Why not using the Wiley so much for transformers is because they have different labelings for the winding parameters, and I can't bother translating from one to another too much. But if you read it and understand it, it is basically talking about the same thing. It's just that they use different labels for their parameters. Right. So to avoid the confusion, I just stick to one or two books. All right. So if there are no further questions, we can finish up here. And next week we'll finish up single phase transformers. So we'll look at efficiency. I think we'll look at efficiency. Efficiency can be calculated in a number of ways. One of the way would be to use the test that we would have done in the lab, the open circuit and short circuit test. By the way, those tests can also help us to calculate the voltage regulation. So you will get those lab data later on in the semester.
Sir, how have you test them, sir? How you look so far? Are you not started?
Boy, regretfully, I have not started. Yeah, and I must apologize. I'm trying to keep my head above water. I actually have 3 modules and I have to be preparing. I spend most of my time trying to prepare notes for each of the classes. So I just running from one thing to the other. But I hope to start marking more consistently over the next maybe next week or so. Hopefully within the next week or so.
Okay, so in regards to the lab, you said 4 persons per group, right?
Yeah, man. I hope you have handed in the first lab already.
Yes, sir. 2 hours we do it. So what? Let me just make the other person on the team. But we named upon the paper.
Yeah, man. That's all right. Yeah, ideally it will 4 because it will give me less to mark. I used to the issue with marking already. If it was, so this is one of the issue with the that I have with the online. It's much harder to mark online. So if it was face to face and you had handed in, you would have gotten back much of your work already. So this is not usual for me. You would have probably gotten back most of your work already within 2 weeks. But I guess it is what it is.
Sure.
But I hope to make sure that by the time you get into finals, you know exactly where you are in terms of everything.
So you decided if we're gonna come in to the final or we're gonna do it online.
No, it's gonna be online. It's gonna be online.
Or through everything we're going on with the pandemic.
Well, yeah, that, but yeah, I think we can actually work out a way for do it online. My only concern, the concern that I've been seeing with the online is that persons may still have some issues with communication or connecting to the Google Classroom. So there might be some delays in handing in. Really, the delays for this class hasn't been bad, but my 2 other classes have been really, really bad. And for the lab 2 that you sent, we should still use the original results. Yeah, the results. Did I send a result for lab 2? I'm not sure if I did. I doubt if I did. But if you use the results that you had among your group members, so you can just use one of them from the from your group, one set of results from the group to do the lab. All right. All right, so that's it for today. If there are no other questions, then I think we can call it a night and try to work these problems in the book and review the notes. Oh, I saw. I actually was looking at the mid-semester test for some people, and I realized that some persons really have not read the notes because I think we had a Delta circuit. People were working. I saw at least 1 or 2 people working it as a star system, and I'm wondering how could they have gotten it so wrong, because the circuit was actually drawn for you. So I don't know.
Sir, one next question. Do we not get penalized with diagram? Because whenever I don't have to draw about the diagram, it just work.
Penalize, that's a strong word.
As in, we don't lose mark.
It depends on what was required. I think in that open delta problem, you needed to have indicated how currents were flowing for you to calculate. So we had started out with a delta, and then we remove one of the resistor. You would have needed to show how you would come by the values of the currents that you have. So a diagram would have helped with that. you couldn't talk your way through that. I wouldn't understand anything.
Sir, question about the one thing about that question. Sir, when we do the open delta, we're supposed to change the shape of the delta.
How you mean?
Because back from slide 1, you said that when it was just 2, I think the angle between them is 90.
No, man, it was a 3-phase system still. I mean, the problem is it's a 3-phase system. Only thing we did was take out one phase out of the load.
The phase, it don't affect the shape or the angles between them.
No, it does not. Remember, the supply voltage is what give you those angle, the voltage, not the impedance.
Oh.
So the impedance now will help to determine the angles for the current, both the magnitude and angle of the current.
So it's still 120 apart.
The voltages, yeah. The supply voltage didn't change. So that is an understanding that you need to have, right? The supply voltage didn't change. Only thing we did was to change one phase of the load. All right. So remember now, we did a 3-phase. Right. We did a 3-phase delta system in the lab, you know. Now, some of you didn't turn on all your lamps at the start. So in some cases, when all the lamps were off, all the loads, you didn't see any current, right? In some cases, you maybe have turned on 2 of the lamps. So basically what we have simulated, it was turning off the switch of one of the phases. So basically that's what we did in this problem. All right. So the supply voltage didn't change. So that is how you link it now back to what we did in the lab. The supply voltage didn't change. So remember, once you set the supply voltage, what you did was actually measure now each of the phases, right? Hopefully, ideally, they should have been balanced, but we know that some of them weren't. It wasn't really balanced in terms of magnitude, but we assume that the angles were still 120 degrees apart. So basically, what we would have done, we wouldn't have changed the voltage again. What we did in this case, in the test, was to just turn off one of the switches. So one of the bulbs would have got out. Basically, that's what we did in that problem. All right. And that circuit now would have been described as an open delta. But the supply voltages haven't changed. Neither them phase angle or magnitude or anything like that. All right. But I was concerned when I saw that there were some persons who were working it as if it was a star system. And I'm thinking, so maybe the only explanation for that was that they didn't read their notes. And probably wasn't coming to the classes and paying attention. But even if you weren't paying attention in class, you have the notes. So just go back and read them over. Do the practice questions that we have been doing. And you should be all right. Okay.
All right, so have a good day.
All right. Okay, everybody. Take care.
All right, sir.